Standard reduction potential, okay? So another term that some people were confused on. So the definition of reduction potential is a parameter to determine the direction of electron flow in a coupled redox reaction. Or another way to think of this is a measure of the tendency to be reduced. Okay, how likely is this metal, or when we talk about our biological examples, this protein or this small molecule, how likely is it to get reduced? Okay, then calculating reduction potential lets us figure out which way electrons would go if we put a pair, a redox couple together. Okay. So to determine the standard reduction potential, we want to start with 1 molar solutions on either side of our electrochemical cell. Okay. What you will do then is connect some external power supply, and you will measure the voltage that you need to exactly oppose the current that was being generated by the cell. All right? And so essentially when you get that zero current flow, whatever voltage reading you have is your potential difference. Okay? Here's a nice table that you will have to read both for your homework, for the practice problems in class today, and it will be given to you for the final exam room. What am I saying? So yes, you'll be given this table. You'll also be given the biological half reaction table, which we will show. Okay, so you might have to like read off of it to get your values. So here it has standard reduction potentials. These are all written in the reduction direction. Okay, now some of these would rather be oxidized, but all of these are written as a reduction reaction. Okay, so that's why it's called standard reduction potential, and that's how you'll always see it. And again, standard here is talking about, we're looking at 1 molar solution. Now the other important thing here is that these are all half reactions. So they're only showing the zinc reduction. But this setup obviously has 2 cells going on. Half cell potentials are measured relative to a standard hydrogen electrode, where we let that be 0 volts. Okay? So the hydrogen electrode potential is in the middle. Okay? And if you measure them all relative to hydrogen, you can put them on this list. We almost never can measure things in absolute in experimental studies. It's very difficult. We almost always set ourselves a standard and measure things relative to it. Okay? And whatever that standard is, we just make sure everybody uses it so that we can compare our data and have it be meaningful. Okay? So when you look at this table, they're almost always organized in this direction. I did find a website when I'm like looking for other resources for you guys that flipped it. I don't know why it would do that. Okay? So all these positive standard reductions would be on the top. These are things that would rather be reduced. Okay? Everything on the bottom would rather get oxidized. So if you compare any 2 things on the list, you can kind of look which one's higher. Simply comparing those 2 things to figure out which one is going to be reduced and which one is going to be oxidized when you pair these 2 things together. Another way to maybe think about this is that these raw metals are moving charges an electron, which is negatively charged. Electrons want to go towards positive. For some reason this helps me, and if it doesn't help you, then you can ignore it. Electrons are moving, and electrons want to go towards the positive because they are negative. So electrons want to go onto all of these things that have a positive standard potential. For me, here they would want to go away from this stuff. And so that helps you, that helps you. So for anyone who's confused about interpretation of this table, is this good now? We're more comfortable with how to read it. And again, like I said, you'll always see them written as reduction potentials as opposed to, you won't see the oxidation reaction written in here. Okay. They're all for half reactions. So standard electrode potentials. Each electrode, okay, so this is 1 electrode here, or our half cell, has an electric potential based on the metal that it is. And we can calculate a potential difference, which will determine for us, like I said, which direction are the electrons going to flow, thus which direction is current flowing, opposite direction for this case. Of course, Johnny's not here. He was the one who asked a really good question at the end of class last time. What is right and left? And I was like, it's just convention. It's the one that's literally on the right side. And he's like, what if you just look at it from the other direction? And I was like, don't do that. So there's some new convention that actually makes sense. I'm sure he'll watch this later or see these slides. Reductions at the right, okay? this is the convention that we are always going to use. So the reaction that is the reduction reaction, put it on the right. Draw it on the right, it will always be drawn on the right. This is what the convention is. It's really frustrating that the book just does right and left, when pretty much any resource on the internet does reduction, oxidation, cathode, anode, all of that jazz. Which reminds me, let me go back quickly. Again, that means for convention, reduction's on the right. The cathode is where reduction is happening. The anode is on the left. The anode is where oxidation is happening. Okay? Just because I think I have a problem with like, which was the anode, which one's the cathode, and I want you to label it, so. Okay, so newest convention, reduction at right. So you could then look at this change in potential difference between our two electrodes, or for our entire cell, our full electrochemical cell. It's the reduction minus the oxidation, the cathode minus the anode. Something like that. Okay, I want to point out something very also important. So this here, this delta E cell being equal to E like right side minus the potential of the left side. You're going to use this equation that has the negative sign in the middle when both of these are standard reduction potentials for the half cells. Okay, these are both the standard reduction potentials from the table, right? Just as you read it off the table. Great, easy, we can just read it from the table, no big deal. Even though one of these is getting oxidized, it's not, the direction that that reaction is flowing isn't in the reduction direction, okay? There are other, if you use other resources that either I give you or you find on the internet, you might see this. It's right plus left. This is basically like an extension of Hess's law, if you will. You flip it over, you flip the sign, and now you can add them together. And so I just want to make sure that's clear so that your signs work out and you're getting, you know, because while you're not going to lose a ton of points for me, you always lose a point if you have the wrong sign, plus or minus. So I mean, it's important to know what you're doing. So I will just put that there. Like I said, it's kind of an extension of Hess's law where you could, you know, the sum of the heat of reactions was just all of the reactions added together in the direction they actually go. So, yes?
For the table, it gave the standard reduction potential with the little degree sign. Do we have to be calculating the standard electrode potential?
The word standard will be, yep, in your question. And this is potentially valid if we're not at standard state conditions, right? I mean, this equation still works. And what we're going to show when we do the Nernst potential is how to calculate this, which it's going to look surprisingly like our equation for determining the reaction-free energy, where we had delta G is equal to delta G at standard state plus the reaction quotient piece. It's going to look a lot like that. But for now, yes, like the problem we're about to do, you're going to use the values off the standard table. Yep. And there will always be, you know, the only table I can give is a standard table.
Right.